right, welcome back. Today we're going to be talking about the product topology. Um, just as a little disclaimer, I am not really attempting to teach this course per se. I am still learning the course myself. This is me studying primarily. Um, and we're just going to be going over the product topology. It's section 15 in Munkres Topology, second edition. And with that said, let's go ahead and get her going. So we're going to just kind of kick it off with a definition right off the bat of what the product topology is, right? So we're going to let X and Y be topological spaces. So the product topology on the Cartesian product between X and Y is the topology having as basis the collection B of all sets of form U cross the Cartesian of the form U and V, the Cartesian product between the two, where U is an open subset of X and V is an open subset of Y. All right, so we'll gain some more intuitive sense as to what this really means. I'll go ahead and draw out a visual here in a second as to like what we mean when we say stuff like this. So, but let's first just kind of verify the fact that our claim here that our collection B forms a basis is true. So our first condition is trivial since the Cartesian product of X and Y is itself a basis element, right? Our second condition is pretty easy as well because the intersection of any two basis elements will form another basis element, right? Basically, we're saying that the intersection of two open sets is itself going to be open inside, right? um, let me write that out, actually. Sorry, let me go ahead and write that out. So once again, the first condition is trivial since X and Y, sorry, the Cartesian product of X and Y itself is a basis element. Now, let's say we have, oops, let me get back the pen. So let's say we have U1 with V1, and then we have U2 and V2. Basically, what we're saying here is that if I were to take U1 and V1 and intersect it with U2 and V2, then that's just the same thing as us saying U1 intersect U2, the Cartesian product of V1 intersect V2. And let me kind of drive some intuitive sense behind how that would visually look. So let's say that I have some open interval right here, which I'll call my V2. And then let's say I have some open interval right here, which I will call V1. And once again, let's go ahead and create some open interval here, and let's go ahead and call this U2. And then let's create a smaller one just right here, and let's call this guy U1. So if I were to go ahead and draw some boxes, so if I were to go U1, V1, that's this guy right here. And if I were to go U2, V2, that would give me a box that looks like this. So that would give me that box. And what we get between them is just this shaded area inside of here, right? Something we need to note here is that the collection here does not form a topology on the cross product. The union of two rectangles is not a product of two sets, so it can't belong to our product topology definition. basically saying that like I'm not making these out of rectangles. I'm making them out of just unique sets, right? So like this itself is the formulation of these guys over here, but that's not how I want to define the product topology. But that does leave the question on uh, what can we say if the topologies on X and Y are given by bases, right? Like what if I don't have like the full-blown topology, I just have kind of like the basis portion of it, right? So that brings us into the next theorem. So that's theorem 15.1. If the collection B is a basis for the topology of X and the collection C is a basis for the topology of Y, then the collection D that's composed of the cross product of the basis elements. Sorry, not the cross product. I see the X and I say cross product. I'm so sorry. I meant the Cartesian product. The Cartesian product of the basis elements of B and C is a basis for the topology of X and Y. Sorry, of the Cartesian product X and Y. So um, let's kind of harken back to our lemma 13.2 to kind of show this one out. So just as a reminder, lemma 13.2 says let X be a topological space. Suppose that the collection C is a collection of open sets of X such that for each open set U of X and each X in U, there's an element C of the collection of C such that X belongs to the set C, which is a subset of U. Then the collection C is a basis for the topology of X. You can just go back and rewatch that video. I actually don't have that sheet pulled up handily at the moment. Sorry about that. Did not plan that ahead too well. So if we say we have a set W of X and of the Cartesian product X and Y, and we have a point XY of W, so let me kind of like write this out a little bit, right? So let's say that is a set of this Cartesian product, right? And we have the Cartesian product of their elements is itself inside of W here. So by definition of the product topology, there is a basis element U cross V such that, so basically by that definition of the product topology, there will exist some U Cartesian product V such that X and Y belong to this right here, and we're kind of glancing. I guess I'm kind of glancing over it, but like in reality, U and V are neighborhoods here. So we're basically saying that if I have some sort of topological space going on over here, right, and I have a definition of a point right here, what I'm really doing is I'm creating this little neighborhood around it. Feel free to go back to the definition of neighborhood from analysis, but really we're describing neighborhoods here. But back to this guy right here, that is a subset of W. Now, because the collection B and the collection C are bases for X and Y, respectively, right, just by how we constructed the problem, we can choose a set B from the collection B. So we can choose a B belonging to B like this, right? Such that X belongs to this set B, which is a subset of U, right? So we have, we basically started with our set XY. We basically said that W is a set that is in here. We say that X and the Cartesian product of 2 points, X and Y, have to belong there, right? So by the definition of the product topology, there must exist some neighborhood such that X and Y belong to that neighborhood, which is a subset of that set. And we're going to go ahead and choose a set B such that X belongs to that B, which is a subset of U. And we are also going to choose in the same vein, we're going to choose a C belonging to C such that Y belongs to that C, which is a subset of V. Well, then X, the Cartesian product of my points X and Y, must belong to the Cartesian product of B and C, my basis elements, which in itself is still a subset of W. Thus, my collection D meets the criterion of our lemma 13.2. So our D is a basis for the Cartesian product of X and Y. Now, the example that's given in the book is the product of R with itself. So that's R2, right? So that's just the normal grid that you're very familiar with working with your entire mathematical career. It has basis. It has basis the collection of all products of open sets of R, but the theorem just proved tells us that the much smaller collection of the products A comma B cross product with CD of open intervals in R will also serve as a basis for the topology R2. Each set can be pictured as the interior of a rectangle in R2, thus the standard topology on R2 is just the one we considered from example 2 of section 13. So example 2 of section 13, that just goes back to us drawing those little rectangles that kind of overlap with one another, right? We are going to go back to our definitions here. So Munkres says that it's sometimes useful to express the product topology in terms of a subbasis. So what we're going to do is we are going to create some functions that we call projections. So we're going to have pi1 and pi2. So basically you can imagine this as, if you think back to linear algebra, it's very similar to that. It's basically just the idea of a projection from linear algebra, or maybe Cal 3 if that's where you first saw projections. But we're basically going to just drop a coordinate, right? We're going to squish it down into a particular plane, and we call that a projection. We do specifically use the word onto here. I'll highlight that for us. So we do specifically use the word onto because pi1 and pi2 are surjective. With the exception is if our set is empty, but we don't really care if our set is empty, because then nothing really makes sense with any of these definitions, I should say. One more thing is that if U is an open subset of X, then the inverse of pi is precisely the set U Cartesian product Y, right? Let me give a little bit of a visual representation of what's going on here, and here I'll actually touch on theorem 15.2 and then I'll kind of draw this visual out. So the collection, so this is the sub-basis collection S of the union between the inverse of U unioned with the inverse, the pi2 inverse of V, is a sub-basis for the product topology, right? So let's get a little bit of a visual intuition as to what's happening here. So let me go ahead and draw back out this grid, right? So if I have some open interval U, so this is my open interval U, and then I have some open interval V right here. Oops, I didn't mean to write V twice, I just meant to write it right here. Essentially what's happening is the pre-image, and I didn't draw these lines perfectly, sorry about that. So the pre-image of U would look something like this. And then the pre-image of V, so this is the pre-image of pi2 for V, right? So that's going to look something something along these lines, right? And What we're kind of interested in is this rectangle right here between the intersections of these pre-images. But if we look at our definition of the subbasis, right, like it's the union of the two, not necessarily the intersection of the two. So the union is these two guys right here, right? I hope that makes sense visually speaking. Um, just think of think back to our ideas of analysis where we have images and pre-images, right? Um, yeah, let's think back to like our definitions of like images and pre-images. So um, if I take, so like let's focus kind of like on the image perspective of it. So let's say I have some interval u right here, right? And I apply my pi1 function. So my pi1 function, remember, if I take x and y, I'm going to compress it down to x such that pi1 of x comma y is just equal to my x value, right? So basically, if I have all of these points, you know, like let's say I insert some set u, right? Um, some set u down here. That means everything above this u in this column is getting compressed all the way down. So, sorry, let me bust out a little bit of a different color here, but it's all getting compressed down into just my u value, right? So it's, I guess that visual doesn't isn't the absolute best, but it doesn't matter how tall I get in this column. I'm just basically sending it all back down to the x-axis here. And it would be the same for the visualization of V, where I'm just compressing it all back into the y-axis. So my pre-image is this entire column, right? Everything that got squished down into that axis. So I hope that makes sense on the product topology. Up next will be the subspace topology.